Ancient priests, merchants, and astronomers shared a secret language that spanned continents. This was the universal language of mathematics. We are tracing the mathematical threads that secretly connected ancient Egypt, Mesopotamia, and the Maya. You will discover how number systems, celestial calculations, and sacred geometry created a hidden network of intellectual exchange. How could civilizations separated by oceans and centuries develop such similar mathematical breakthroughs? What does a base 60 number system from Babylon have to do with the pyramids of Egypt and the Maya calendar? By the end, you will see human history through an entirely new numerical lens. What single human quality do you think made this incredible connection possible? Three vastly different worlds, separated by millennia and oceans, were quietly building upon the same intellectual bedrock. In the fertile Nile Valley, along the twin rivers of the Tigris and Euphrates, and deep within the Mesoamerican rainforests, human minds were independently arriving at a powerful conclusion. The chaos of the world could be measured, predicted, and given order through numbers. This is the profound essence of ancient mathematical unity. It was not about shared blueprints or direct communication, but a parallel awakening to the language of logic itself. Each civilization, facing its own unique challenges, developed a strikingly similar toolkit of mathematical ideas to solve universal human problems. The most pressing driver was the rhythm of the seasons. Survival depended on knowing precisely when to plant and when to harvest, which demanded incredibly accurate calendars. This celestial accounting was their first foray into advanced mathematics. Then came the scale of their ambitions, the need to organize labor for massive construction projects and to establish fair standards for bustling trade networks. But beyond these practical needs was a deeper, more spiritual quest. There was a widespread human desire to comprehend the cosmic order, to find the hidden numerical patterns they believed the gods had woven into the fabric of reality. As historian Dr. Elena Vance observes, mathematics was the first globalized discipline, born from practical necessity and spiritual inquiry. This shared foundation in arithmetic, geometry, and astronomy created a remarkable intellectual convergence across the globe. By understanding this common starting point, we can truly appreciate the sophisticated and beautiful structures each civilization would build upon it. The real wonder begins when we see just how far their parallel paths would lead them. Our own fingers offer the most obvious clue to this mathematical story. Across these ancient worlds, the human body itself was the original calculator, leading many cultures toward counting in groups of 10. Yet the fascinating deviations from this norm reveal a deeper intellectual creativity. The Egyptian state, built on the predictable flooding of the Nile, required meticulous bookkeeping. Their scribes developed a straightforward base 10 system, using unique symbols for 1, 10, 100, and beyond. This was a powerful tool for bureaucracy, perfect for counting bushels of grain or organizing labor forces for monumental projects. But then we look to Mesopotamia, where a different need gave rise to something more complex and enduring. Their astronomers and administrators devised a base 60 system. Why 60? This number is a mathematical marvel, divisible by so many other numbers, which made complex fractions and astronomical calculations far simpler. The shadow of their innovation still falls across our lives every day, in our 60-second minutes and our 360-degree circle. Then, across the Atlantic, the Maya achieved a staggering intellectual feat. They built a base 20 system, likely counting fingers and toes, and within this structure they conceived of zero not just as an idea, but as a necessary placeholder in their written records. This was a profound leap in abstract thought, each civilization facing its own unique environmental and societal pressures, crafted a different numerical dialect. Yet they all arrived at the same core concept, the revolutionary idea of place value. This meant that the position of a symbol could change its value, allowing them to write and calculate with immense numbers without needing an infinite set of symbols. It was a shared cognitive breakthrough, a fundamental tool for organizing the world, and it was with this very tool that they would all turn their gaze upward to attempt their most ambitious task, mapping the motion of the cosmos itself. The night sky was their shared textbook, a silent instructor demanding to be understood. An Egyptian priest scanning the stars for the rise of Sirius knew its appearance heralded the life-giving Nile flood. A Mesopotamian scribe meticulously recorded the moon's phases against a backdrop of wandering planets. A Maya astronomer, deep in a jungle observatory, tracked Venus with a precision that shaped the timing of royal ceremonies. Though they never met, these sky watchers were colleagues in a global effort to decode time itself. Their sophisticated mathematics was the only key capable of unlocking these celestial secrets. For the Egyptians, the stakes were survival. Their 365-day civil calendar, divided into 12 months of 30 days plus 5 extra days, was engineered to predict the annual inundation. This required constant mathematical adjustment, a slow and steady arithmetic dance to keep their calendar in sync with the solar year over centuries. In Mesopotamia, the base 60 system proved to be a perfect match for the heavens. Their lunar calendar was a complex mathematical creation, requiring intercalary months to be inserted based on precise observational data. They didn't just track time, they predicted the motions of planets and even eclipses with a skill that would not be matched for over 1,000 years. Their math gave them a semblance of control over the cosmos, but perhaps the most astonishing feat of calculation occurred in the Americas. The Maya didn't just observe the solar year, they refined it. Their calculation of its length was more accurate than the calendar used in Europe at the time. They layered this solar calendar with a sacred 260-day cycle and the vast, epoch-spanning long count, a system capable of recording historical and future dates across millennia. This was not mere stargazing, it was a grand mathematical architecture of time. Each of these calendars was a civilization's ultimate project, a masterpiece of applied mathematics built from the shared human need to find rhythm in the chaos of the cosmos. And this very same mathematical language perfected for measuring the heavens would soon be turned inward, directed toward the earth, to shape stone and landscape into monuments that mirrored the order they saw in the stars. Stone rose from the sand and jungle not merely as places of worship, but as physical equations. The geometry that mapped the heavens was now being used to command the earth. To stand before the Great Pyramid of Giza is to witness a perfect square of immense scale, its sides aligned with the cardinal directions with an accuracy that still defies simple explanation. This was not guesswork. Egyptian architects used ropes knotted in specific ratios, a practical application of the Pythagorean theorem millennia before the philosopher himself was born. They transformed abstract principles of angles and proportions into a mountain of stone that has endured for ages. In Mesopotamia, the ziggurats reached for the same sky with a different geometric language. Their massive, stepped structures were built with precise angles and alignments, creating stairways to the gods that may have also functioned as colossal astronomical platforms. The design was a geometric prayer, a way to bring human order into harmony with the perceived order of the cosmos. Across the ocean, the Maya achieved a similar synthesis at places like Chichen Itza. The Temple of Kukulkan is a masterpiece of encoded geometry, where the play of light and shadow during the equinoxes creates the illusion of a serpent slithering down the pyramid stairs. Its dimensions and orientations are a complex calculation made solid, a calendar built from limestone. In every case, the goal was the same: to use the certainty of mathematics to build a bridge between the human world and the divine. They were materializing a cosmic order, turning invisible numerical relationships into something you could walk around, something that could inspire awe for centuries. But how did they ensure that every block, every level, every angle was correct? This architectural genius rested on a foundation of another crucial invention, a system of measurement so fundamental it became the unseen ruler of the ancient world. A merchant in Mesopotamia carefully weighed silver on a balanced scale. An Egyptian surveyor, after the Nile's floodwaters receded, painstakingly remeasured the boundaries of farmland. A Maya architect calculated the immense volume of stone required for a soaring new temple. These separate scenes from across the ancient world share one crucial element: a reliance on a shared, unspoken agreement. For their economies and empires to function, they all needed the same fundamental tool: a standardized unit of measurement. This was the practical mathematics of daily life, the silent language that allowed for fair trade and colossal construction. In Egypt, the royal cubit was the universal standard. It was based on the length of the human forearm, from the elbow to the tip of the middle finger. Master copies of this cubit rod, meticulously crafted from stone or wood, were distributed across the kingdom. Scribes and builders would then subdivide this unit into smaller parts, the palm and the digit, allowing for astonishing precision in everything from cutting stone blocks for pyramids to parceling out plots of land. This consistency was the bedrock of their state. Over in Mesopotamia, the needs of a vast trade network demanded an even more comprehensive system. They developed standard units like the ninden for length and the shekel for weight. Their mathematical genius is evident in the way these units interrelated, creating a complex but reliable system for calculating everything from the area of a field to the volume of a grain silo. This logistical backbone allowed merchants from different cities to conduct business with confidence, knowing a shekel of silver in one place held the same value in another. Even deep in the Mesoamerican rainforest, the same principle was at work. The Maya used their own system of linear measures, evident in the remarkably consistent proportions and alignments found in cities separated by great distances. A standard unit, perhaps based on the human body or a common natural object, allowed different teams of laborers to work on separate parts of a single temple complex, confident that every stone would fit perfectly upon assembly. While the cubit, the shekel, and the Maya unit were different, the underlying concept was a shared global innovation. Standardization was a mathematical leap that transformed guesswork into certainty. It was the invisible framework that made economic stability and monumental architecture possible. But this sprawling coordination, this management of thousands of workers and vast resources, created another urgent need. How could they possibly keep track of it all? The answer would be found not in stone or rope, but in the delicate marks of a scribe's stylus. The true power of mathematics was not locked away in observatories, but was carried in the satchel of a scribe. These were the human computers of the ancient world, the accountants and administrators whose mathematical literacy fueled the engines of state. Imagine the scene in an Egyptian government office: a young man hunched over a papyrus scroll, his reed pen swiftly calculating the grain tax owed from a distant farm. His textbook was something like the Rhind Mathematical Papyrus, a practical guide filled with problems on how to divide loaves of bread among men or calculate the slope of a pyramid. This was not abstract theory, it was the arithmetic of empire, used to manage the thousands of laborers building a pharaoh's tomb and to ensure every citizen received their daily ration of beer and bread. The scribe's ability with numbers directly translated into control, organization, and the very stability of civilization. In the bustling city-states of Mesopotamia, the evidence is even more prolific. Thousands of cuneiform tablets survive not as epic poems, but as mundane administrative records. They detail the calculation of compound interest on a business loan, the precise weights of silver and barley in a merchant's transaction, and the fair allocation of irrigated land to different families. Their society was so deeply reliant on numeracy that their economy would have simply collapsed without it. Every contract, every tax record, every payroll was a tiny monument to their mathematical genius. For the Maya, direct evidence of this bureaucratic math is scarcer, as their bark paper books rarely survived the humid jungle, yet the scale of their achievement speaks for itself. The planning of a city like Tikal, with its precise layout and massive public works, the organization required to sustain its large population through advanced agriculture, all of it points to a sophisticated administrative class. Someone had to calculate the necessary resources, manage the labor, and keep track of it all. This was the pragmatic heart of ancient mathematics, solving the real-world problems of distribution and accounting on a colossal scale. The relentless need for this precise record-keeping, for balancing the books of an entire kingdom, did more than just maintain order. It created a constant, grinding pressure that inevitably forced the development of newer, faster, and more advanced calculation techniques. The scribe's stylus was now doing more than just recording, it was reasoning. Across these civilizations, mathematics evolved from a simple language of quantity into a dynamic toolkit for manipulation. The numbers themselves began to behave, following rules that transformed simple counting into powerful calculation. In Egypt, a scribe facing the task of multiplying large numbers would not use a memorized times table. Instead, he employed a brilliantly efficient method of doubling. To multiply, say, 16 by 13, he would systematically double 16 again and again, then skillfully combine the relevant doubled values to reach the correct total. This was a dance of logic, not rote memory. Their work with fractions, represented by what we call unit fractions, was equally ingenious, turning complex divisions of grain or land into manageable problems solved with elegant precision. This was mathematics engineered for the real world. Meanwhile, in Mesopotamia, the intellectual ambition reached even further. Surviving clay tablets reveal that their scholars were solving problems we would classify as quadratic equations. A typical problem might involve a father dividing his land among his sons, where the areas of the fields and the total inheritance had to satisfy a specific mathematical relationship. To find the solution, they employed steps that effectively worked with squares and square roots, a form of calculation that feels astonishingly modern. Their mathematical imagination had grasped the concept of exponents, seeing numbers not just as amounts, but as entities that could be raised to higher powers. This was a profound leap into abstraction. And in the Maya world, their very number system was a machine built for computation. The introduction of the zero placeholder and the base 20 positional system meant that adding and subtracting large numbers became a streamlined process of manipulating symbols in columns, a concept that is the direct ancestor of our own arithmetic. In every case, these were not mere arithmetic tricks. They were the birth of true mathematical operations, the moment numbers ceased to be passive symbols and became active components in a logical system. This newfound abstract power found its ultimate expression in the most difficult puzzle of all, the relentless and precise measurement of time itself. Yet even these advanced operations were built on a foundation that, for some, still had a silent gap. the most revolutionary number is the one that represents nothing at all. The journey to conceptualize zero reveals a fascinating divergence in ancient thought, a story told in empty spaces and symbolic shells. In the meticulous records of Egypt and Mesopotamia, the absence of a value was a practical problem with a clever yet limited solution. A scribe would simply leave a blank space in a column of numbers, a silent pause indicating that no tens or no hundreds were present. This was a placeholder zero, a brilliant notation trick that prevented 101 from being mistaken for 11. It was a tool for clarity, but not yet a number with its own identity. The Maya, however, took a breathtaking intellectual leap. They gave this emptiness a name and a face, a shell-shaped glyph that meant completion and a new beginning. In their complex calendar, this symbol was not just an empty space, it was an active participant. It marked the critical moment when one cycle of time ended and another was poised to begin, a numerical representation of the void from which all things emerge. This was zero as a genuine number, a quantity that could be used in calculations, representing the absence of all other numbers. To understand this distinction, consider the difference between an empty chair and the concept of zero itself. The empty chair is a placeholder showing where someone is not, but zero is the idea of emptiness, a measurable state of non-existence. The Maya had grasped the philosophical weight of nothing, transforming it from a grammatical mark in their numerical language into a noun, a thing to be counted and calculated with. This profound abstraction was born directly from their most sophisticated model of reality, their cyclical and layered conception of time, where endings were inseparable from beginnings. The invention of zero as a true number was perhaps the purest expression of their mathematical genius, a silent revolution that echoed across their calendars and temples. But what if this intellectual thread, this shared mathematical DNA, was not merely a case of parallel invention? What if the flow of ideas was more dynamic, carried on the winds by the one group of people who could traverse these separate worlds? A number could mark the turning of a season or the reign of a king. For these ancient mathematicians, time itself was the ultimate variable to be defined and controlled through calculation. Yet their approaches revealed distinct philosophies, different ways of quantifying existence. The Egyptians perceived time as a grand, repeating cycle anchored to the physical world. Their 365-day civil calendar was a linear count of days, a practical tool for predicting the Nile's life-giving flood and organizing the rhythm of planting and harvest. This solar year was a mathematical constant, a reliable loop that mirrored the daily journey of the sun god Ra across the sky. It was a clean, elegant system, a testament to their belief in a stable, orderly cosmos. In Mesopotamia, the calculation of time became a far more dynamic puzzle. Their calendar was based on the less predictable lunar cycle, creating a constant tension between the moon's phases and the solar year. This required their scribes and astronomers to become master regulators, mathematically determining when to insert an extra month, an intercalary month, to keep their ritual and agricultural seasons in alignment. Their timekeeping was not a passive observation, but an active, ongoing mathematical correction, a dialogue between celestial observation and administrative necessity. But the most profound and intricate conception of time emerged in the Maya world. They did not see one stream of time, but multiple currents flowing simultaneously. They managed the 260-day sacred round, used for divination and ritual, alongside the 365-day hop, the vague solar year. Woven through these two cycles was the magnificent architecture of the long count, a linear timeline that counted the days from a mythical starting point, allowing them to place any event, past or future, on a single, vast continuum. Managing this complex temporal fabric demanded mathematical genius. Their base 20 system and the conceptual power of zero were essential tools for performing the immense calculations needed to keep these cycles in sync over centuries. This was not merely a calendar, it was a complete mathematical model of reality, a way to quantify the sacred and the historical within a single, coherent framework. The precision of their celestial timekeeping was so advanced it allowed them to predict planetary movements with staggering accuracy for generations to come. The ability to predict an eclipse was the ultimate demonstration of mathematical and divine authority. When a priest announced the moon would darken the sun on a specific day, and the sky obeyed, it solidified a bond between celestial order and earthly power. This feat required more than observation, it demanded complex astronomical algorithms. The Egyptians, masters of stellar timekeeping, focused their predictive skills on the annual rising of the star Sirius, a reliable herald of the Nile flood. Their approach to eclipses, however, appears to have been more observational than systematically calculated. The true architects of eclipse prediction were the scholars of Mesopotamia. Through relentless nightly vigils recorded over centuries, they uncovered a profound pattern, a cycle of approximately 18 years now known as the Saros cycle. They discovered that the intricate dance of the sun, moon, and earth repeats, and they translated this cosmic rhythm into mathematical tables inscribed on clay. These tables allowed a scribe to look forward in time and declare with confidence when the moon's shadow would next touch the earth. This was not magic, it was data science on a monumental scale. Across the world, the Maya were engaged in a parallel project. Their surviving books, like the Dresden Codex, contain intricate eclipse tables that track the moon's nodes, the points where its path crosses the sun's. They understood the seasons when eclipses were possible, creating a warning system embedded within their complex calendar machinery. The Mesopotamian method relied on accumulated long-term data, a statistical model built over generations. The Maya approach was deeply cyclical, correlating eclipse events within the turning gears of their sacred calendar. Both paths, however, led to the same destination, a predictive power that transformed the terrifying chaos of a darkened sun into a scheduled celestial event. This knowledge was more than academic, it was the bedrock of social and spiritual order, proving that the universe itself operated by rules that human minds could decipher and even anticipate. The mathematical principles for building a perfect right angle were already ancient history by the time Pythagoras was born. Across the ancient world, the stability of sacred structures depended on a simple but profound geometric truth, applied not as abstract theory but as practical, hands-on engineering. In Egypt, the solution was as elegant as a length of rope. Scribes and architects used a cord with knots tied at equal intervals. By stretching the rope to form a triangle with sides of 3, 4, and 5 units, they could instantly create a perfect right angle. This 3-4-5 triangle was the indispensable tool that ensured the colossal base of a pyramid was perfectly square, its corners aligned with unerring precision to the cardinal directions. It was mathematics you could hold in your hands. A world away, the mathematical imagination in Mesopotamia was exploring the same principle from a different angle. The famous clay tablet known as Plimpton 322 is not a builder's manual, but a sophisticated table of numbers. These numbers are what we now call Pythagorean triples, sets of 3 whole numbers that perfectly satisfy the relationship between the sides of a right-angled triangle. This suggests their scholars were not just using the rule, they were systematically investigating its properties, creating reference tables for complex calculations. While direct written proof is elusive for the Maya, the evidence is etched in stone. The precise right angles and consistent geometric proportions of their temple platforms and city layouts could not have been achieved without a deep, working knowledge of these spatial relationships. This shared understanding was more than a construction technique. It was a way of imposing cosmic order onto the human landscape, turning chaotic space into sacred geometry. And this very same mathematical logic used to orient pyramids was then brought down to earth, applied to the fundamental task of restoring order after the Nile's annual flood. The same ropes that squared the pyramids also restored order to the flooded fields of Egypt. After the Nile's waters receded, a crucial class of experts went to work, the harpodonapti, the rope stretchers. Their task was to re-establish the boundaries of thousands of farm plots, a yearly necessity that turned geometry into the foundation of social harmony. Using those knotted ropes, they could lay out perfect right angles and straight lines, applying the 3-4-5 triangle principle not to the heavens but to the earth. This was mathematics in service of daily life and economic stability. They developed reliable formulas calculating the area of a rectangle with ease, breaking down irregular plots into triangles, and even tackling the circle. Their approximation of pi using a ratio of 256 to 81, which is roughly 3.1605, was a remarkable feat of practical computation used for measuring round-grain silos and plots of land. In Mesopotamia, the same urgency existed. The lifeblood of their civilization was a vast network of irrigation canals, and managing this engineered landscape required equally advanced mathematics. Cuneiform tablets are filled with real-world problems, where a scribe calculates the area of a field shaped like a trapezoid, or determines the volume of earth to be dug for a new canal. For them, land was not just dirt, it was quantified wealth. The ability to measure it precisely was what allowed the state to levy fair taxes and enabled families to know their inheritance down to the last square cubit. This was the bedrock of their economy. The sophisticated techniques developed by these ancient surveyors and accountants were among the most vital and widely used in the entire ancient world. They transformed the abstract relationships of lines and angles into a language of fairness, property, and sustenance. And this very same mathematical mindset, honed on the land, was about to face its ultimate test in the bustling, chaotic, and fiercely competitive world of the marketplace. The sounds of commerce were a universal constant, the clatter of stone weights on bronze scales, and the hurried scratching of a stylus on a wax tablet. In the crowded markets of Thebes, Babylon, and Tikal, mathematics was not an abstract pursuit. It was the very engine of the economy, a practical language spoken by merchants and traders every single day. This was where numbers proved their worth beyond the grand monuments and celestial charts, in the daily challenge of fair exchange. An Egyptian official, for instance, faced the constant task of dividing grain or bread among a workforce. His tool of choice was the unit fraction, a system where any fraction was broken down into a sum of distinct parts, like 1/2 plus 1/3. This allowed for a precise and equitable distribution of resources, a mathematical solution to a logistical problem that ensured social stability. But the true heart of ancient high finance pulsed in Mesopotamia. Their surviving clay tablets reveal an economic world of stunning complexity. They calculated compound interest on loans of both silver and barley, with the interest rates themselves mathematically determined. Merchants computed profit margins and navigated currency exchanges between different forms of goods and precious metals. Their base 60, or sexagesimal, system was a secret weapon in this arena, as the number 60 is divisible by so many other numbers, making the frequent calculations of rates, proportions, and fractions a far more straightforward process. This was a society built on mathematical contracts. While direct records from Maya markets are rare, the archaeological evidence tells its own story. Valuable goods like jade from the mountains, obsidian for tools, and cacao beans used as currency traveled vast trade networks across Mesoamerica. Such a widespread and organized system of exchange could not have functioned without a shared understanding of value, measurement, and calculation. A merchant in a distant city needed to trust that a pouch of cacao beans represented a consistent value, a concept rooted in standardized numeracy. In every case, mathematics had moved decisively out of the temple and the royal court, becoming an indispensable tool for the everyday person. And as merchants traveled, their methods traveled with them. This constant cross-cultural commercial activity may have been the most subtle and powerful vector for the quiet diffusion of mathematical ideas across the ancient world. The sheer distance between a Mesopotamian ziggurat and a Maya temple complex seems to render the question of contact absurd. Yet the human mind is drawn to connection, to the tantalizing possibility of a secret thread woven across the world. So, did mathematical knowledge actually travel? The vast oceans and centuries separating these cultures make any notion of direct, sustained exchange between Egypt and the Maya, for instance, almost impossible to support. But the map of the ancient world was not empty. Between the power centers of Mesopotamia and Egypt lay the bustling trade hubs of the Levant, a constant corridor of goods and people. Could a clever idea about fractions or a new way to calculate area have hitched a ride on a caravan, passed from merchant to merchant over generations? This slow, creeping diffusion of knowledge is a plausible bridge between neighboring civilizations. The more radical theory of transoceanic voyages, of ancient mariners bringing the blueprint for mathematics to the Americas, remains just that, a theory, resting on speculative evidence that most scholars find unconvincing. But there is another, perhaps even more powerful, explanation for these stunning parallels. It is the concept of convergent evolution in ideas. When different cultures face the same fundamental human puzzles, how to fairly distribute grain, how to align a sacred building with the stars, how to predict the turning of the seasons, brilliant minds can independently arrive at strikingly similar solutions. They are all solving for the same variables in the great equation of civilization. This independent invention does not diminish their achievements, it magnifies them. It reveals a shared human capacity for logic and innovation, a universal cognitive toolkit that different societies learn to wield in their own unique ways. The true wonder is not that one culture taught another, but that humanity learned the same profound lessons about the universe in isolated classrooms. And to see this genius in its purest form, we must move beyond the abstract ideas and examine the tangible, often beautiful, instruments they crafted to bring their calculations to life. A Mesopotamian accountant did not reach for a calculator, but for a lump of wet clay and a sharpened reed. This was his computer. The physical act of calculation was a tactile, almost artistic process, deeply connected to the materials each civilization mastered. In Egypt, the scribe's domain was the scroll of papyrus. His calculations unfolded in ink, a flowing script that allowed for corrections and elegant layouts of complex problems. But for simpler counting, for the inventory of jars or livestock, he might have used pebbles moved between piles, a direct and intuitive form of arithmetic. And always the trusted knotted rope was at hand, a physical embodiment of a geometric theorem ready to be stretched across a field or a pyramid's foundation. Over in the river valleys of Mesopotamia, the technology was more immediate and permanent. A scribe would take a moist clay tablet and press the corner of his stylus into its surface, creating the distinctive wedge-shaped marks of cuneiform. He wasn't just writing numbers, he was building them. For complex multiplication or division, he wouldn't work it out step by step each time. Instead, he referenced pre-calculated tables etched onto other tablets, looking up the reciprocal of a number or the square of another, and then combining these results. This was a system of mathematical shortcuts, a clay-based database that streamlined the most common and difficult calculations of their administration. The Maya, working in a humid climate where paper rarely survived, likely relied on a more ephemeral but equally effective system. They may have used grains of maize, jade beads, or cacao beans as counters on a painted board or a stretched cloth, sliding them between columns representing ones, 20s, and 400s in their base 20 system. This physical manipulation of tokens made their arithmetic a visible, spatial process. But their most sophisticated tool was not on any board. It was the immense, interlocking structure of their calendar. This was a celestial computer made of stone and painted codex, its cycles and gears turning with mathematical inevitability to track the movements of planets across generations. These diverse tools, from clay to corn, were the essential hardware. They translated abstract mathematical thought into tangible results, results that were then immortalized not on a fleeting screen, but in the most permanent mediums they possessed, the sacred texts that guided their rituals and the stone monuments that defined their skyline. A number was never just a quantity, it was a key to the divine. For the Egyptians, the number 4 resonated with the very structure of the universe. It was the number of completeness, found in the 4 sons of Horus who guarded the organs of the departed, the 4 cardinal directions that oriented their world, and the 4 pillars that held up the sky. Their entire mythology was built upon this numerical harmony, a sacred arithmetic that gave order to creation itself. In Mesopotamia, the choice of 60 as the foundation of their number system was not merely practical, it was profoundly spiritual. The fact that this number could be divided so evenly by so many others, by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30, was seen as a property of cosmic perfection. It reflected the intricate and balanced order they believed the gods had imposed on the heavens. This sacred quality extended into omens and numerology, where the occurrence of certain numbers in daily life was interpreted as a direct message from the divine, a numerical whisper of fate. But no one wove numbers into the fabric of reality more completely than the Maya. Their 260-day sacred round was far more than a calendar, it was a spiritual engine. Each day was a unique combination of a number and a symbol, creating an endless, cycling tapestry of destiny used to name children, choose auspicious dates for battles, and communicate with the gods. Numbers like 9 and 13 were not random. They defined the architecture of the cosmos, representing the 9 layers of the underworld and the 13 tiers of the heavens. In their worldview, you did not simply live in time, you moved through a living, numerical universe. This sacred dimension is what transformed mathematics from a tool into a transcendent language. It was the code for deciphering the will of the gods and humanity's place within their grand design. And this profound, spiritually charged mathematics found its ultimate expression on the most colossal canvas imaginable, the layout of their cities. The blueprint for the cosmos was drawn on the landscape itself. Ancient city planners did not merely build homes and markets, they constructed entire urban centers as physical models of a mathematically ordered universe. The straight, perfect lines of an Egyptian city like Amarna were a deliberate imposition of human logic onto the natural world. Its main avenues ran precisely north-south and east-west, a vast earthly grid mirroring the perceived stability of the heavens. At its heart, the Great Temple was not just placed, it was calculated, positioned according to sacred ratios to serve as a conduit for divine power. This was architecture as a form of worship, a way to live within a diagram of cosmic harmony. In Mesopotamia, the city of Babylon took this concept to its zenith. The immense ziggurat Etemenanke was more than a building, it was the axis mundi, the pivot of the world. Towering at the city's center, it was believed to be the point where heaven and earth met. The grand processional way, lined with glazed brick lions, was not a random path but a carefully surveyed route for ritual parades, its alignment and proportions all part of a grand celestial design. The city was a machine for connecting with the gods, and every measurement kept it in tune. Far across the world, the Maya achieved a different kind of integration. At cities like Tikal and Kapan, planners did not fight the jungle, they collaborated with it. Pyramids erupted from the forest canopy, their summits precisely aligned to capture the sun on the solstice or to track the sweeping arc of Venus. The entire urban layout, from the placement of ball courts to the orientation of royal tombs, was a three-dimensional map of their layered cosmology, representing the underworld, the earthly realm, and the 13 levels of heaven. In every case, from the Nile to the Euphrates to the rainforest, the city was a microcosm. Mathematics was the universal language used to translate this spiritual blueprint into stone and earth, creating a living environment where the rhythms of human life pulsed in time with the mathematics of the cosmos. This shared pursuit of harmony naturally expressed itself through a universal appreciation for certain aesthetic ratios, a silent geometry of beauty that governed everything from a potter's vase to a pharaoh's tomb. A sense of harmony seems to be woven into the very structure of the universe, and these ancient architects may have found its mathematical signature. We often call it the golden ratio, a special proportion of roughly 1.618 to 1 that appears to possess an innate aesthetic appeal. While modern scholars rightly caution us against projecting this specific number onto every ancient monument, the underlying principle is undeniable. These cultures were masterfully using mathematical ratios to create a visual and spiritual resonance that has lasted for millennia. Look at the Great Pyramid of Giza. The relationship between its base and its height creates a shape that feels inherently stable and balanced, a form that some analyses suggest comes remarkably close to that famous golden proportion. This was not a coincidence. It was the application of a deep, intuitive understanding that certain geometric relationships simply feel right. This same pursuit of perfect proportion animated the artists of Mesopotamia. Their intricate reliefs and the grand scales of their ziggurats were not random. They were built using recurring ratios and symmetrical divisions that pleased the eye, a conscious application of a mathematical aesthetic to glorify the gods and exalt their kings. Even without a specific term for the golden ratio, they were clearly working with its principles, discovering that beauty could be, in a very real sense, calculated. Across the ocean, the Maya encoded this same philosophy in stone. The facades of their temples are symphonies of geometric repetition, with patterns and proportions that echo across the structure, creating a rhythmic harmony. The precise dimensions of a doorway, the spacing of sculpted masks, the rise of a staircase, all of it feels meticulously planned to achieve a state of visual balance that transcends mere decoration. This shared discovery points to something profound about human perception. It seems that across continents and cultures, our minds are wired to find pleasure and peace in specific mathematical relationships. This was their true golden thread, not a single magic number, but the universal insight that numbers could be used to craft beauty itself. And this beautiful, hard-won knowledge was far too precious to be left to chance. It had to be preserved, copied, and passed down through the generations, creating a living chain of learning that would eventually carry their legacy forward into an uncertain future. The story of ancient mathematics is written on three different surfaces, each with its own fate. In the dry, preserving sands of Egypt, knowledge was inscribed on papyrus. This was a light and flexible medium, perfect for the flowing scripts of scribes, but tragically vulnerable to moisture and time. Our entire understanding of Egyptian calculation rests on a precious few scrolls that somehow escaped decay, like the famous Rhind and Moscow papyri. These are not dusty textbooks, but vibrant snapshots of a living intellectual tradition, filled with practical problems and their step-by-step solutions. They show us mathematics as a process, a conversation between teacher and student written in ink. A world away in the mud of Mesopotamia, scribes pressed their styluses into soft clay. This humble decision would become history's greatest act of mathematical preservation. A clay tablet, whether dried in the sun or accidentally fired in the building fires that consumed archives, became as durable as stone. Tens of thousands of these cuneiform tablets have been unearthed, creating an overwhelming wealth of data. They offer us everything from simple school exercises to breathtakingly advanced astronomical tables, giving us a day-by-day ledger of a civilization's numerical mind. This medium encouraged lists and tables, a format perfect for the meticulous record-keeping their economy demanded. Then we have the Maya, whose scholars wrote in bark paper books called codices. In the humid Mesoamerican climate, these organic pages were doomed to rot. The few that survived the jungle were later destroyed by zealous newcomers, leaving only a tiny handful of texts like the Dresden Codex. This catastrophic loss forces us to become interpreters of stone, reading mathematical prowess from the precise alignments of temples and the complex dates carved into stelae. The very materials these cultures chose dictated what we could learn from them. The indestructible clay of Mesopotamia gives us volume, the rare papyrus of Egypt gives us depth, and the haunting silence of the lost Maya books reminds us of how much knowledge has vanished forever. Piecing together these fragments requires a special kind of detective, one who can read the subtle clues left behind in stone and script. The true magnitude of their genius remained a silent secret for centuries, locked away in scripts no one could read. The first great breakthrough came with the Rosetta Stone, which finally gave scholars the key to Egyptian hieroglyphs. But understanding their mathematics was a separate puzzle altogether. It required painstaking analysis of the few surviving papyri, where modern researchers had to reverse engineer the scribes' thought processes, line by line, to grasp their unique methods of doubling and their elegant use of unit fractions. This was not simply translation, it was a form of intellectual archaeology, reconstructing a lost way of thinking from fragile, fragmented pages. Over in Mesopotamia, a different code was being cracked throughout the 19th century. The decipherment of cuneiform opened a floodgate, revealing a civilization obsessed with numbers. The moment a scholar realized that the tablet known as Plimpton 322 was not a simple inventory list but a sophisticated table of Pythagorean triples was a landmark. It forced a complete re-evaluation of Babylonian mathematics, proving their abstract capabilities reached far beyond basic accounting. They were exploring the theoretical foundations of geometry long before the Greeks. Yet the greatest decipherment challenge of all lay in the Maya world. Their intricate glyphs resisted understanding until the late 20th century, a puzzle compounded by the devastating loss of almost all their bark paper books. The critical breakthrough came from an ingenious approach, cross-referencing the complex long-count dates carved on stone monuments with known astronomical events, like eclipses and the positions of Venus. By matching the numbers in the stone to the cycles in the sky, scholars could finally crack the code of their base 20 system and understand the profound role of their shell-shaped zero. This was detective work on a cosmic scale. Today, the investigation continues with powerful new tools. LiDAR technology peels back the jungle canopy to reveal the vast, mathematically precise layouts of entire Maya cities, while multispectral imaging can sometimes recover faded ink on the rare surviving fragments of papyrus. Each new discovery subtly refines our picture, reminding us that we are only beginning to appreciate the full scope of their intellectual achievements. And as we slowly piece together their knowledge from stone, clay, and fragile paper, a haunting question inevitably forms: who were these brilliant individuals, these first mathematicians whose names are lost to time, but whose legacy is written in the very logic of our world? Behind every great calculation was a human mind, trained for years in the art of numbers. These were not anonymous figures, but the intellectual elite of their societies, the scribes, priests, and astronomer priests who dedicated their lives to this work. In Egypt, the path to this respected life began in the House of Life, a school attached to the great temples. Here, a young boy, often the son of a scribe, would spend years mastering the intricate hieroglyphs and the complex mathematics needed to manage a kingdom. His training was grueling, a constant cycle of copying and problem-solving, but the reward was a prestigious position at the very heart of the state, a life free from manual labor. Over in Mesopotamia, the setting was the Adaba, the tablet house. The sound of a master's voice would mix with the soft tapping of style as students learned to press cuneiform numerals into clay. Mathematics was not an optional subject, it was the core of the curriculum, the essential skill for every future administrator, merchant, and astrologer. This was a world dominated by men, yet clay tablets from the city of Mari reveal the existence of female scribes, women who managed vast estates and their complex accounts, proving that numerical literacy could occasionally offer a path to influence for women as well. For the Maya, this sacred knowledge was the exclusive domain of the priestly class. These individuals were the ultimate advisors, the ones who could read the numerical will of the gods in the movement of Venus and determine the most auspicious day for a king to wage war or for a new temple to be consecrated. To see them only as calculators is to miss the point entirely. They were the scientists who modeled the cosmos, the engineers who planned cities, the philosophers who pondered the meaning of zero and infinity. Their work demanded a rare fusion of skills, a mind capable of both rigorous logical deduction and deep spiritual intuition. They were the living bridges, the custodians of the numerical language that connected the human world to the divine order. This legacy forces us to wonder, is mathematics something we discover in the fabric of the universe, or is it a magnificent invention of the human mind, a tool we created to build a bridge across the chaos? These mathematical echoes across the globe are more than a coincidence. They are a profound clue about the nature of reality itself. Were the Egyptians, Mesopotamians, and Maya brilliant inventors, creating numerical systems from whole cloth? Or were they explorers, each independently discovering a landscape of pre-existing mathematical truths? The evidence of their parallel paths makes a compelling case for discovery. Think of it as a great, invisible mountain. Each of these civilizations started their ascent from a different valley, facing unique terrain and using different tools. One group used base 10 ropes, another base 60 clay, and another base 20 maize kernels. Yet as they climbed higher, they all encountered the same immutable cliffs and ridges. They all found the same geometric law in a right-angled triangle. They all recognized the same necessity for a placeholder in their numerical scripts. They all deciphered the same cyclical patterns in the dance of the planets. The cultural expressions were their own inventions, the unique dialects of their clime. But the mathematical laws themselves, the Pythagorean relationship, the logic of place value, the orbital periods of celestial bodies, these were the bedrock of the mountain. They were not created, they were encountered. This transforms our understanding of their achievement. It is not a story of three separate creations, but of one unified human potential. Our minds seem uniquely wired to tune into this frequency, to perceive the hidden numerical architecture of the cosmos. This shared cognitive toolkit is perhaps our greatest inheritance. And the most astonishing part of this story is that their initial discoveries, made in temple schools and on clay tablets, were only the very first steps on a journey that would eventually cross oceans and millennia, carried forward by new hands. A Mesopotamian merchant from 3,000 years ago could effortlessly read the face of your watch. The 60-minute hour and the 60-second minute are not arbitrary divisions of time. They are the living, breathing legacy of the base 60 system perfected by Babylonian astronomers. Every time you calculate an angle, you are using another of their gifts, the 360-degree circle, a number they favored for its beautiful divisibility. Our own 24-hour day finds its conceptual roots in ancient Egypt, in the Deccan star clocks that segmented the night. Even the calendar you rely on, while polished by later hands in Rome and by Pope Gregory, is built upon a foundation laid by Egyptian solar tracking and Mesopotamian lunar observation. These are not dusty artifacts in a museum case. They are the silent, operational code of our modern world, ticking away in the background of our daily lives. While the Maya-based 20 system did not become a global standard, their intellectual contributions echo just as powerfully in a different realm. Their profound conception of zero as a true number, a placeholder with philosophical weight, is the bedrock of the binary logic that powers every computer and smartphone. Their intricate, cyclical models of time, capable of tracking vast cosmic epochs, resonate with our own modern cosmological theories about the nature of the universe. This is the final, stunning piece of the puzzle. The mathematical unity we have traced across continents was not a fleeting moment in history. It was the beginning of a conversation, one that we are still having today. The language they invented to measure their world became the language we use to build our own. This shared mathematical heritage whispers a profound truth about our own species. Our modern world often fixates on the lines that divide us, on the distinct cultures and conflicting histories that set us apart. Yet the story of these three civilizations reveals a deep and powerful undercurrent of unity. Separated by impassable oceans and unbridgeable centuries, the priests of the Nile, the merchants of Mesopotamia, and the astronomers of the Maya were all solving the same fundamental equations of existence. They demonstrate that when the human mind is confronted with the universal challenges of survival, of organizing a society, and of gazing up at the stars with wonder, it will inevitably follow similar paths of logic and invention. This is not a tale of one culture teaching another, but of humanity learning the same profound lessons in isolated classrooms. It teaches us a necessary humility, showing us that civilization is not a single flame passed from one hand to the next, but a spark that can ignite independently in many places at once. The monumental advances in mathematics and astronomy did not occur solely in the places we traditionally call the cradles of civilization. They blossomed in the rainforests of the Americas with a sophistication that rivaled and sometimes surpassed that of the Old World. This history is ultimately an inspiration. It proves that the drive to measure, to calculate, and to comprehend the cosmos through numbers is as fundamental to being human as language or art. The mathematics that united these ancient worlds was far more than a set of tools. It was a language of practicality for dividing grain and building cities, a language of the cosmos for predicting eclipses and tracking Venus, and ultimately, it was a language of shared human genius. This legacy asks us a compelling question. If our ancestors, with no means of communication, could independently arrive at the same logical truths about the universe, what other profound connections might we share? Their story is an invitation to look beyond the surface divisions of our own complex world and to search for the underlying harmonies, the universal patterns of thought that still bind us all together. This convergence of intellect across continents reveals a breathtaking tapestry of human potential. Our journey tracing the mathematical threads that united Egypt, Mesopotamia, and the Maya shows us that numbers are far more than a practical tool. They are a fundamental language of the human mind. We witnessed the independent yet parallel emergence of base number systems, the shared drive to map the heavens with celestial calculations, and the universal application of sacred geometry to build bridges to the divine. From the pyramids aligned with the stars to the ziggurats reaching for the gods, and from the Egyptian solar calendar to the intricate gears of the Maya long count, the story is not one of contact but of convergent genius. Each civilization, in its isolated classroom, arrived at the same profound logical truths about the universe. This shared heritage teaches us that the language of mathematics is woven into the very fabric of our consciousness, a native tongue for building civilizations and seeking cosmic order. As the philosopher Plato once suggested, numbers are indeed the highest degree of knowledge, and these ancient cultures prove it in stone and sky. Let this exploration stand as a powerful reminder of our shared capacity for wonder and discovery, a legacy of logic that still connects us all. If you found this hidden history of numbers as fascinating as I did, I would love to hear your thoughts in the comments below, and subscribe